we're going to use one that has the 3 parts since we need to do our diagram of for before, during, and after. This is what, 7.58, I think it is. All right, so we have Brittany stands at rest on a skateboard. Combined mass of Brittany on the skateboard is this. Dave tosses this big of a pumpkin to Brittany, and when she catches it, she and the skateboard begin to roll backward with the speed of this. So if we had to categorize this as a type of collision, what type of collision would you say it was? Right, inelastic, because the 2 bodies become one afterwards. Since Brittany, the skateboard, and the skateboard are really one object, then your other object is the pumpkin. All right, so I might actually even put that into my y, that it's an inelastic collision. So of course, momentum is conserved in system. Therefore, my system would be Brittany and the pumpkin, and that probably would be enough to get for the written part. And of course, I'm going to want to do my diagram. So beforehand, I have Brittany on the skateboard, the pumpkin. During, I have her on the skateboard, the pumpkin in contact with her. And then afterwards, kind of looks very similar to my during. And then I get into my momentum vector. She wasn't moving, so she has none. The pumpkin is going to have a momentum of the pumpkin that way. And then afterwards, we're going to have the momentum after, I'm going to call it Brittany and the pumpkin. During this, there's going to be an impulse on Brittany, and therefore there has to be an equal and opposite impulse on the pumpkin. And that would give me full credit for my y. So then I would move on to my how. And because it's a conservation of momentum problem, I'm going to grab my conservation of momentum equation. And it'd probably be good to remind myself what the definition of momentum is. And so now I've got those to use over here in my how part. And beforehand, I'm going to have, let's see, before I'll have the momentum of Brittany and the momentum of the pumpkin. They're separate bodies. And then together afterwards, I'm going to have the momentum of Brittany and the pumpkin together because they become one body. All my momentums are pointing to the left, so I'm going to say that's positive. And so my momentum of Brittany before, she's not moving, so I know that's 0. Momentum of the pumpkin would be the inertia of the pumpkin and the velocity of the pumpkin, and that's to the left, so that's positive, so I'm just going to call that the speed of the pumpkin. Afterwards, I'm going to have the inertia of Brittany and the inertia of the pumpkin together, and the speed, and I'm predicting it's in that direction. So again, a positive of Brittany and the pumpkin together. And now it's just a factor of plugging in my values that they gave me and calculating for the value that they wanted. So they told me that Brittany and the skateboard is 53 kilograms, the pumpkin's 3.7, and they roll backwards with a speed of 2.6, and they want to know the original speed of the pumpkin. So I'm putting in the inertia of the pumpkin, 3.7 kilograms, velocity of the pumpkin, which is what I don't know. Here I'm going to have 53 kilograms and my 3.7 kilograms. And then they tell me that this was 0.26, 0.26 meters per second. Rearrange and solve for velocity of the pumpkin, and you'll be all set. So I hope that made sense. All right, so let's see. We have the first narrative. Puck A is this. It's moving towards puck B with this. It's initially at rest. Velocity of this to the left, velocity to the right. And they want to know the speed of one of them before the collision, the change in kinetic energy of the total system that occurs during the collision. All right. So, it is one that's before and after. So, what was this? What did we label this? Collisions and one. So, we have a before and after situation. I would probably start off with the system is the two pucks. And then go on to momentum is conserved in system. And I would probably express something along the ways that I realized to make sure I knew that momentum is a vector. So direction matters. There we go. So that's probably what I'd write, and then I would do my drawing. Let's see, we have one puck, second puck, and then they're gonna hit each other, and then they're gonna separate again after that. And so let's see, we want to label them moving towards puck B. So I'm going to call this one puck A. And this one B. So while they're in the beginning, before anything happens, puck A has a momentum in that direction. Puck B has no momentum. Then afterwards, they tell us after collision, puck A has a velocity to the left. Yeah, so I'm going to call this direction left. Make my life easier. They had them obviously the other way. So this will be the momentum of A afterwards, and then B moving to the right. That will be the momentum of B afterwards. And then in between here, we have an impulse on A in that direction. It had momentum in that way, now it's got momentum in that direction. And we have to have an equal and opposite momentum impulse on B in that direction. So that's my, that would give me full credit on the Y. Yeah, that would work. So switching over to my how, it's another conservation momentum problem. So I need to grab my conservation of momentum again. I think I'll skip grabbing the definition of momentum this time. I'm sure that you guys know it by now because you've used it so often. So beforehand, my system, I have the momentum of A and the momentum of B. Afterwards, they're still separate, so I have a new momentum for A plus a new momentum for B, noticing that those are vectors because the arrow's on the top. I'm going to call I'm going to call to the right here as positive. We'll make to the right positive and to the left negative. So my momentum of A beforehand is going to be positive because it's pointing to the right. And so that's just going to give me momentum of A. My momentum of B beforehand is 0, since it's not moving. Afterwards, my momentum of A is pointing to the left. So that means it's a negative momentum. So I'm going to put it as negative there. And B is pointing to the right. So it's going to give me a positive there, where I've defined positive and negative. And then I can go my next step, inertia of A, the speed of A beforehand, then negative, the inertia of A, the speed of A afterwards, plus the inertia of B, speed of B afterwards. And now it's time to fill in some of my values. I want the speed of A before. So my mass of A is 0.247 and mass B is 0.375. So I can start to fill those in. I remember them. 2.47. Or is it 0.247? 0.247. A. And afterwards, I think they told me what the velocity, what the speed was afterwards. After the collision, puck A has a velocity of 0.123 meters per second to the left. So I already take the left into account with the negative out front here. 0.1, whoops. 0.123 meters per second. I'm going to run out of space here, so just move down a little bit. And puck B has a velocity of 0.653. So the inertia of B, they told me also 0.375 times that velocity that they just told me, 0.653. And solve that for VA to get my first answer. So let's see. I thought it was going to be here. Grab my calculator. And I can, if I want to get, might as well do the whole left side, right? Negative 0.247 times 0.123 plus 0.375 times 0.653. That's the whole right-hand side. And if I divide that by 0.247, I get my VA, which is, should be 0.868 meters per second. It's good to check that at this point. It's a multi-part problem. Yep. Two numbers that I'm adding on the bottom. I ran out of room because I wrote so big. So it's the second, it's the mass of B and the velocity of B. Mm-hmm. Sure. That's fine. Okay, you can do that. And then, okay, so that got part A for us, right? And then we want to go on to do part B, where they're asking the change in the total kinetic energy of the system during the collision. we need to send our page here. We need the definition of kinetic energy to use. It's right up here on our equation sheet. And if we remember, change is always final minus initial, right? You know, if you spend 20 bucks, it's you take how much ever you have left and subtract 20 from it. So the change in the kinetic energy here is going to be KE final minus KE initial. And we're going, at the end, we have two objects moving. So we need the kinetic energy of A after the collision, plus the kinetic energy of B after the collision. We'll subtract that from all the kinetic energy of the system before the collision, which is the only one that was moving was A. So you have kinetic energy here of A. And now it's an apply your equation, 1/2 inertia of A, velocity prime squared of A, plus 1/2 inertia of B, velocity prime of B, minus 1/2 inertia of A, velocity of A squared. So you're just applying your definition of kinetic energy. No.
The kinetic energy of A at the end is not the kinetic energy of I.
Right. Mm-hmm. Yeah. And now you're just substituting in, let's see, the inertia of A was 2.247, right? And the velocity of A beforehand, oh, that was my 0.8684 squared, and I should have meters per second there and kilograms here. Excuse me. 1/2 inertia B, which was 0.375. 0.375 kilograms. Velocity of B, oh wait a minute, I just made a mistake. This velocity is the velocity of A afterwards, or the speed of A afterwards. And that one I was told, that's not the one I solved for. I was told that one. After the collision, puck A has a velocity of 0.123, so this should be 0.123 meters per second. B is 0.653, 0.653. Of course, you could do each of these separately and then add them all together. I just, I don't know, given the type of calculator I tend to use, I tend to do everything all at once. Kilograms. And then now this is what it had beforehand, which was 0.8684, bless you, squared. And now I just do all of that in my calculator. So, you guys need me to put it in the calculator, or you think you can put it in your own? Sure, I'll put it. 0.5 times 0.247 times 0.123 squared plus 0.5 times 0.375 times 0.653 squared minus 0.5 times 0.247 times 0.8684 squared I get a negative answer, which means there's less kinetic energy after the collision than before, which is usually the case. Negative 0.011, and that would be in joules. So I should check that that answer is correct. And if it is, then I'm happy. Let's see. Negative. Incorrect. Uh-oh. Where did I make the mistake? Yes, ma'am. Yeah.
Is it, could you do it like breakfast stuff so that it wasn't, because is that squared?
I feel pretty good about my order of operation.
What?
I feel pretty good about my order of operation.